Imagine standing on a world where the sun appears 3 times larger than it does from Earth, where the ground beneath your feet is hot enough to melt lead, and where there is no atmosphere to shield you from the cosmic fury above. Now imagine another world, shrouded in toxic clouds, where the atmospheric pressure would crush you instantly and the temperature could vaporize metal. These places exist. They orbit our sun alongside Earth, yet they became something entirely different. Tonight, we journey to Mercury and Venus, the scorched worlds that could have been our home. What cosmic accident made Earth a paradise while these became infernos? Let's find out together. Our solar system is a place of extraordinary diversity, but nowhere is the contrast more striking than in the inner realm. Here, closest to our star, 4 rocky worlds orbit in a delicate cosmic dance. You know Earth, of course, your home, a world of water and life. And you've likely heard of Mars, the rusty desert world that whispers of ancient rivers. But between Earth and the Sun lie 2 mysterious siblings, Mercury and Venus. These are the forgotten worlds, the scorched planets that most of us never think about. Yet their stories are among the most fascinating in our solar system. Tonight, you and I will visit them both, and in doing so, we'll discover why Earth is so remarkably rare. Mercury and Venus are Earth's closest planetary neighbors, yet they might as well exist in entirely different universes. Mercury, the smallest planet in our solar system, races around the sun every 88 days, forever locked in the star's scorching embrace. It's a world of extremes. Venus, on the other hand, is Earth's twin in size, but there the similarity ends. Beneath its beautiful pearlescent clouds lies a nightmare realm of crushing pressure and temperatures that would make hell seem pleasant. How did these 2 worlds, born from the same cosmic cloud as Earth, become such radically different places? To understand these worlds, we must travel back more than 4.5 billion years to a time when our solar system was nothing but a swirling disk of gas and dust. Within this primordial chaos, tiny grains began to stick together, forming pebbles, then boulders, then mountains of rock and metal. Closer to the newborn sun, where temperatures were highest, only materials that could withstand intense heat survived. Lighter elements like hydrogen and helium were blown away by the solar wind, leaving behind heavy metals and rocky minerals. This is why Mercury, Venus, Earth, and Mars are all rocky planets, unlike the giant gas worlds farther out. But location would determine everything. In those early, violent days, the inner solar system was a shooting gallery of destruction. Planetesimals, objects ranging from meters to hundreds of kilometers across, smashed into each other with devastating force. Some collisions destroyed both objects, scattering debris across space. Others merged, creating ever larger bodies. Mercury and Venus were forged in this cosmic furnace, each impact adding mass and heat. But they faced different challenges. Mercury, being closest to the sun, experienced the most intense bombardment and the strongest solar winds. Venus, just slightly farther away, grew larger and retained more of its volatile compounds. Even at birth, their fates were beginning to diverge. As millions of years passed, the chaos gradually subsided. The largest bodies had swept up most of the available material in their orbital zones, and the frequency of catastrophic collisions decreased. What emerged were the worlds we know today, but they were very different from their current states. Young Mercury may have had a thicker rocky mantle and perhaps even a thin atmosphere. Young Venus might have been more Earth-like, with water vapor in its atmosphere and possibly even liquid water on its surface. But the sun's relentless radiation and the subtle differences in their distances from our star would set them on radically different evolutionary paths. The inner sanctum was about to become a tale of two destinies. Before we journey to these worlds individually, take a moment to appreciate what we're about to explore. We're going to visit places where the concept of habitables has no meaning whatsoever, where the very definition of hostile is redefined. Yet in understanding why these planets are so alien and uninviting, we gain profound insight into why Earth is so precious. We learn what makes a world livable and what cosmic factors had to align perfectly for life to flourish. Mercury and Venus are not failed Earths. They are laboratories that teach us about planetary evolution, about the fragile balance required for habitability, and about our place in this vast cosmic arena. So settle in, let your mind expand beyond the familiar confines of Earth, and prepare for a journey that will take you closer to the sun than you've ever imagined. We'll feel the scorching heat of Mercury's eternal day. We'll descend through Venus's toxic clouds to a surface no human could ever walk upon. And we'll emerge with a new appreciation for the cosmic lottery that made our own world a haven for life. The scorched worlds await. Our journey begins now as we accelerate away from Earth and set our course for the innermost planet of all. The swift messenger, Mercury. As we leave Earth behind and accelerate inward toward the sun, the first thing you notice is the light. It intensifies with every passing hour, growing brighter and harsher. The comfortable yellow glow that illuminates Earth becomes a searing white radiance that seems to penetrate everything. This is the realm of Mercury, where the sun dominates the sky with an intensity impossible to fully comprehend until you've witnessed it yourself. Mercury orbits at an average distance of just 58 million kilometers from the sun, less than 40% of Earth's orbital distance. At this proximity, solar radiation is more than 6 times stronger than what Earth receives. We're entering a realm where the sun is not a gentle life-giver, but a cosmic furnace. Mercury has fascinated humanity for millennia. The ancient Greeks knew it as two different objects, Apollo when it appeared in the morning sky, and Hermes when it graced the evening. Eventually, they realized it was a single celestial body, the fastest moving planet visible to the naked eye. The Romans renamed it Mercury after their messenger god known for his speed, and the name fits perfectly. Mercury completes an orbit around the sun in just 88 Earth days, moving through space at an average velocity of 47 kilometers per second. It's racing around our star faster than any other planet, trapped in a tight orbital embrace by the sun's immense gravitational pull. But here's something strange. This swift world rotates on its axis incredibly slowly. While Mercury races around the sun, it rotates on its axis at a glacial pace. One complete rotation takes 59 Earth days. This creates a peculiar relationship. Mercury rotates exactly 3 times for every 2 orbits around the Sun, a phenomenon called a 3002 spin-orbit resonance. The result is a bizarre day-night cycle unlike anywhere else in the solar system. A single day on Mercury from one sunrise to the next lasts 176 Earth days, exactly 2 Mercurian years. Imagine that for a moment. If you stood on Mercury's surface and watched the sun rise, you would have to wait the equivalent of nearly 6 Earth months before it rose again. During that time, Mercury would have traveled around the sun twice, and you would have experienced 1 full day. As our spacecraft draws closer, Mercury begins to reveal its true face. From a distance, it appeared as a simple grey sphere, but now we can see it's heavily cratered, bearing the scars of billions of years of cosmic bombardment. The surface is remarkably similar to our Moon, covered in impact craters of every size imaginable. There are smooth plains that formed from ancient lava flows, and there are enormous impact basins created when asteroids the size of mountains slammed into the young planet. Mercury has no atmosphere to speak of, just a thin exosphere of atoms knocked off the surface by the solar wind and micrometeorite impacts. This means every single meteorite that comes Mercury's way strikes the surface unimpeded, creating yet another crater in an already battered landscape. Look at the Terminator, the line separating Mercury's day side from its night side. On the sunlit hemisphere, surface temperatures soar to a staggering 430 degrees Celsius, hot enough to melt lead, tin, and zinc. The rocks themselves glow with radiant heat. But follow that line to the night side, and the temperature plummets to minus 180 degrees Celsius, colder than anywhere on Earth's surface. This is a temperature swing of more than 600 degrees, the most extreme in our solar system. Without an atmosphere to distribute heat, each side of Mercury exists in its own temperature extreme. The day side bakes under relentless solar radiation, while the night side radiates all its heat away into the cold vacuum of space. It's a world of unimaginable contrasts. Despite being the smallest planet, only slightly larger than our Moon, Mercury has one of the highest densities of any object in the solar system. This tells us something profound about its composition. Deep within Mercury lies an enormous iron core that makes up an astonishing 70% of the planet's mass and accounts for 85% of its radius. By comparison, Earth's iron core represents only about 32% of our planet's mass. Why does Mercury have such a disproportionately large metallic heart? This is one of the great mysteries we'll explore shortly. But first, let's descend to the surface itself and stand in a place where few spacecraft have ever ventured and where no human will likely walk for centuries to come. We make our final approach to Mercury's surface, selecting a landing site near the Terminator where temperatures are less extreme. As we descend, the cratered landscape rises to meet us, and the scale of this ancient world becomes apparent. Some of these craters are billions of years old, formed when the solar system was young and violent. They've remained virtually unchanged since the day they formed because there's no wind or water to erode them, no tectonic activity to reshape them. This is a frozen moment in geological time, a window into the solar system's distant past. Our landing struts touch down gently on the regolith, the layer of loose, fragmented material covering the surface. We've arrived at Mercury. Let's explore this scorched world together. Standing on Mercury's surface is like standing on a more extreme version of the Moon. The sky above you is utterly black. There's no atmosphere to scatter sunlight and create the blue sky you're accustomed to on Earth. Stars are visible even during the day, though they're overwhelmed by the sun's brilliance. And that sun? It dominates the sky in a way that's both beautiful and terrifying. From Mercury's surface, the sun appears about 3 times larger in diameter than it does from Earth, a bloated disk of searing light that commands your attention. You can feel its radiation pressing down on you, an almost physical force. If you were standing here in just a spacesuit, the suit's cooling systems would be working at maximum capacity to keep you alive. The surface beneath your feet is covered in a fine grey powder regolith created by countless meteorite impacts over billions of years. Each impact, from the smallest micrometeorite to the largest asteroid, has pulverized the rock, creating this layer of loose material. It's similar to lunar regolith, but slightly different in composition. Mercury's regolith is darker, reflecting only about 12% of the sunlight that hits it, making Mercury one of the darkest planets despite being so close to the sun. Pick up a handful and let it sift through your gloved fingers. Each grain is a piece of Mercury's ancient history, a fragment that has possibly remained undisturbed for billions of years. In the harsh sunlight, some of the mineral grains sparkle faintly, tiny crystals catching the light. Look around at the landscape. In every direction, craters upon craters stretch to the horizon. Some are small, just a few meters across, the result of relatively recent impacts. Others are enormous, kilometers wide, with raised rims and central peaks where the crust rebounded after the impact. The shadows they cast are absolute, pitch black in contrast to the brilliantly lit surfaces. There are no halftones here, no gentle gradients, just extreme light and extreme shadow. This harsh lighting reveals every texture, every detail of the surface. You can see where smaller craters have superimposed themselves on larger, older ones, creating a complex tapestry of overlapping impact, scars that planetary scientists call the impact record. This record tells the story of Mercury's violent past. In the distance, you can see scarps, long, winding cliffs that cut across the surface, sometimes for hundreds of kilometers. These are called lobate scarps, and they're one of Mercury's most distinctive features. They formed when Mercury's interior cooled and contracted, causing the crust to buckle and crack like the skin of a drying apple. As the iron core solidified, the entire planet shrank by about 7 kilometers in radius, and these scarps are the wrinkles that resulted. Some of them tower more than a kilometer high, immense walls of rock that have thrust older craters upward and cut through plains. They're evidence that Mercury is geologically dead now, but it wasn't always so. Billions of years ago, this world was volcanically active, its interior churning with heat. Among the countless craters, one dominates all others. The Caloris Basin, over 1,500 kilometers in diameter, is one of the largest impact structures in the entire solar system. It formed about 4 billion years ago when an asteroid, perhaps 100 kilometers across, slammed into Mercury with unimaginable violence. The impact was so powerful that it created shockwaves that traveled through the entire planet, emerging on the opposite side and creating a region of chaotic, jumbled terrain. Standing at the rim of Caloris, you would be unable to see the opposite rim because it would lie beyond the horizon. The basin's floor has since been filled by ancient lava flows, creating smooth plains that contrast with the heavily cratered terrain surrounding it. This is geology written in stone, a catastrophic moment frozen in time. Walk toward a crater rim and peer over the edge into its shadowed interior. Surprisingly, some of these permanently shadowed craters near Mercury's poles harbor a secret water ice. Yes, water ice on the hottest planet in the solar system. This seems impossible, but it's true. These polar craters are so deep and their rims are so high that sunlight never reaches their floors. In these eternal shadows, temperatures remain perpetually below -170 degrees Celsius, cold enough to trap and preserve water ice for billions of years. This ice likely came from comets that struck Mercury over the ages. It sits there still, hidden in darkness, while just meters away, the sunlit surface bakes at temperatures that would vaporize any exposed ice instantly. Even on this scorched world, pockets of frozen water persist. As you stand here on this alien surface, watching the enormous sun slowly track across the black sky, you might wonder what it would be like to experience a Mercurian day from beginning to end. Remember, one day here lasts 176 Earth days. The sun rises slowly, taking weeks to climb from the horizon to its zenith. But here's something even stranger. At certain points in Mercury's elliptical orbit, the sun appears to reverse its motion in the sky. It stops, moves backward for a few Earth days, then resumes its forward motion. This retrograde motion is caused by Mercury's peculiar combination of orbital speed and rotation rate. It would be a slow, surreal dance, the sun performing impossible movements against the backdrop of stars. Mercury is a world where nothing behaves as you would expect. Beneath your feet, below kilometers of ancient rock and impact, shattered crust, lies Mercury's greatest mystery, its enormous iron core. This metallic heart is so massive that if you could somehow remove all of Mercury's rocky outer layers, the core alone would be larger than Earth's moon. The core's radius is about 2,000 kilometers, while the entire planet is only about 2,440 kilometers in radius. This means the core takes up an overwhelming percentage of the planet's interior. Why? Why does this small planet have such a disproportionately large iron core compared to every other rocky planet? The answer to this question has puzzled planetary scientists for decades, and it takes us back to Mercury's violent formation in the early solar system. There are three main hypotheses for Mercury's metal-rich composition, each involving catastrophic events. The first suggests that after Mercury formed with a more normal ratio of metal to rock, a massive collision with another planet-sized body occurred. This impact was so violent that it stripped away much of Mercury's rocky mantle, leaving the metal-rich core relatively intact. The vaporized and molten rock from the collision was scattered into space, never to return, while the dense iron core remained. This would be similar to the collision that formed our moon, except instead of creating a satellite, it created a stripped-down planet. It's a violent origin story, but the early solar system was a place of unimaginable destruction where collisions of this magnitude were not uncommon. The second hypothesis involves the young sun's intense heat and radiation. In the earliest days of the solar system, the sun was more active and energetic than it is today. Mercury, being so close, would have been subjected to intense solar radiation and powerful solar winds. These forces could have vaporized and blown away the lighter, rocky components of Mercury's crust and mantle, leaving behind the heavier iron, which was much harder to dislodge. Over millions of years, this process could have stripped away a significant portion of Mercury's silicate rock, concentrating what remained into the iron-rich world we see today. It's a slower, more gradual process than the collision hypothesis, but no less dramatic in its ultimate effect on the planet's composition. The third possibility is that Mercury simply formed from material that was naturally rich in metals and poor in silicates. In the innermost regions of the protoplanetary disk, closest to the hot young sun, temperatures were so high that only the most refractory materials, those with the highest melting points, could condense and form solid particles. Iron and other metals would have condensed, while lighter silicates remained vaporized and were blown outward to cooler regions. Mercury, forming in this metallic-rich zone, would have incorporated more iron from the very beginning. Each of these hypotheses has evidence to support it, and the truth may involve a combination of all three. Mercury's formation was likely influenced by multiple factors, each contributing to its current composition. What we do know is that Mercury's core is not entirely solid. It has a liquid outer portion surrounding a solid inner core, much like Earth's core structure. We know this because Mercury has a magnetic field, albeit a weak one, only about 1%, the strength of Earth's magnetic field. This magnetic field is generated by the dynamo effect, the circulation of electrically conductive liquid iron in the outer core, driven by heat from the inner core and the planet's rotation. The existence of this magnetic field came as a surprise when NASA's Mariner 10 spacecraft discovered it in 1974. A small planet like Mercury should have cooled enough by now for its entire core to be solid, yet the magnetic field proves that at least part of the core remains molten even after 4.6 billion years. The presence of a partially molten core tells us something profound about Mercury's interior dynamics. The planet must have some mechanism for retaining heat, preventing it from cooling completely. One possibility is that the core contains sulfur, which would lower its melting point and allow iron to remain liquid at temperatures where pure iron would solidify. Another possibility is that heat is still being generated within the core through radioactive decay of elements like uranium and thorium. Or perhaps the insulating effect of the rocky mantle is more efficient than we thought, preventing heat from escaping. Understanding Mercury's thermal evolution is crucial to understanding its current state and its past. This tiny planet, battered and scarred, still harbors an active metallic heart. NASA's Messenger mission, which orbited Mercury from 2011 to 2015, revolutionized our understanding of this world's interior. The spacecraft's instruments measured tiny variations in Mercury's gravitational field and its rotation rate, allowing scientists to infer the size and state of the core with unprecedented accuracy. Messenger discovered that Mercury's solid inner core has a radius of about 2,000 kilometers, while the liquid outer core extends several hundred kilometers farther out. The mission also revealed unexpected concentrations of volatile elements on the surface, potassium, sulfur, and sodium elements that should have been baked away by the sun's heat. Mercury continues to surprise us, revealing that even the most extreme environments can harbor unexpected complexity. The iron heart beats on, hidden beneath the scorched landscape. Mercury is often described as airless, but this isn't entirely accurate. It does have an atmosphere of sorts, an extremely tenuous exosphere, so thin that it's essentially a vacuum by Earth standards. The pressure at Mercury's surface is about 1/4 of Earth's atmospheric pressure. To put that in perspective, the best vacuum chambers we can create on Earth are still millions of times denser than Mercury's exosphere. This gossamer-thin envelope of atoms extends thousands of kilometers above the surface, but the total mass of all these atoms combined would fit in a small suitcase. What's remarkable is not that Mercury has this exosphere, but how it maintains it and what it tells us about the constant interaction between the planet, the solar wind, and the sun's radiation. Unlike Earth's atmosphere, which is held in place by gravity and consists of molecules constantly colliding with each other, Mercury's exosphere is so thin that individual atoms rarely collide. They follow ballistic trajectories, arcing from the surface up into space and falling back down like tiny, slow-motion meteorites. These atoms don't come from volcanic outgassing as Earth's atmosphere did. Instead, they're constantly being knocked off Mercury's surface by the solar winds, by photons from the sun, and by micrometeorite impacts. Each impact, each energetic solar wind particle, ejects surface atoms into space. Some of these atoms escape Mercury's weak gravity entirely and are lost to space. Others fall back to the surface, only to be ejected again later. It's a constantly replenishing, constantly depleting cycle. The composition of Mercury's exosphere is fascinating. It contains sodium, potassium, calcium, magnesium, hydrogen, helium, and oxygen, among other elements. Sodium is particularly abundant and can actually be detected from Earth using telescopes. When energized by solar radiation, sodium atoms emit a characteristic yellow-orange light, creating a faint glow around Mercury that astronomers can observe. This sodium tail sometimes extends for thousands of kilometers into space, creating a comet-like feature that fluctuates with solar activity. The source of this sodium is likely the minerals in Mercury's crust, liberated by the constant bombardment. By studying the exosphere's composition, scientists can learn about the composition of Mercury's surface without ever landing on it. The exosphere is a window into the planet's chemical makeup. Mercury's magnetic field, though weak, creates a miniature version of Earth's magnetosphere, a bubble that partially shields the planet from the solar wind. When the solar wind encounters Mercury's magnetic field, it's deflected around the planet, creating a bow shock similar to the wake a boat creates moving through water. However, because Mercury's magnetic field is so weak and the solar wind at Mercury's distance is so intense, this magnetosphere is tiny and dynamic. It extends only about 1.5 planetary radii on the day side before being compressed by the solar wind, while on the night side it stretches into a long tail. The solar wind can actually penetrate this weak shield, directly striking Mercury's surface and contributing to the exosphere's formation. Within Mercury's magnetosphere, charged particles from the solar wind become trapped, bouncing back and forth along magnetic field lines in radiation belts similar to Earth's Van Allen belts, but much weaker and closer to the surface. These trapped particles can interact with Mercury's exosphere, causing some atoms to become ionized and creating a very tenuous plasma environment. Occasionally, when solar activity increases and powerful coronal mass ejections from the sun sweep past Mercury, the magnetosphere can be compressed so much that the solar wind directly strikes the surface on the day side. During these events, the rate of surface sputtering increases dramatically, and Mercury's exosphere becomes temporarily denser. The planet is locked in a constant battle with the solar wind, its weak magnetic shield barely holding back the onslaught. One of the strangest features of Mercury's magnetosphere is that it's offset from the planet's center. The magnetic axis is shifted northward by about 500 kilometers. This asymmetry means that the magnetic field is stronger in Mercury's northern hemisphere than in the southern hemisphere, and the magnetic field lines have a peculiar geometry. Scientists are still working to understand why this offset exists. It may be related to the structure of Mercury's core, with the dynamo that generates the field being concentrated in a specific region rather than being evenly distributed. This offset creates regional differences in how the solar wind interacts with different parts of Mercury's surface, possibly explaining why some areas have different exosphere compositions than others. Studying Mercury's exosphere and magnetosphere teaches us about the fundamental processes that occur when a planet interacts with its star. Mercury is essentially a natural laboratory for these space weather phenomena. The intense solar radiation, powerful solar wind, and weak protective magnetic field create conditions that allow us to study magnetospheric physics in their most extreme form. Every particle knocked off Mercury's surface, every trapped ion in its magnetosphere, every time the solar wind compresses the magnetic field. These are all pieces of data that help us understand not just Mercury, but planetary systems throughout the universe. Even this whisper-thin atmosphere has profound stories to tell, if only we listen carefully enough to hear them above the solar storm. As we lift off from Mercury's scorched surface and begin our journey outward, the planet recedes beneath us, once again becoming the gray, cratered sphere we first approached. We've walked on the closest world to the Sun, felt the intensity of solar radiation at its most extreme, and peered into the planet's massive iron heart. Mercury has revealed itself as a world of paradoxes. The hottest and coldest places in the solar system existing side by side, water ice in permanent shadow while the sunlit surface bakes, a tiny planet with a disproportionately huge core, and an airless world with a tenuous but dynamic exosphere. Now, we set our course for the next scorched world, one that couldn't be more different from Mercury despite also being bathed in intense solar heat. We're heading to Venus. The journey from Mercury's orbit to Venus's orbit takes us outward from the Sun, and you can feel the intensity of solar radiation gradually decreasing. Venus orbits at an average distance of 108 million kilometers from the Sun, still close enough to receive about twice the solar energy that Earth does, but nowhere near Mercury's scorching proximity. As we travel, Venus grows from a point of light to a disk, and then something remarkable becomes apparent. Unlike Mercury's bare, exposed surface, Venus is completely shrouded in clouds. Thick, unbroken clouds that swirl and flow in complex patterns. These aren't water clouds like on Earth, they're sulfuric acid clouds, part of an atmosphere so dense and hostile that it makes Mercury's vacuum seem welcoming by comparison. From space, Venus is stunning. The planet shines with an intense, creamy brilliance that makes it the third brightest object in Earth's sky after the Sun and Moon. Its clouds are so reflective that Venus returns about 70% of the sunlight that hits it, compared to Earth's 30%. This high albedo gives Venus its characteristic appearance as the morning star or evening star, the beautiful beacon that has inspired poets and lovers for millennia. The ancient Babylonians, Mayans, Greeks, and Romans all tracked Venus's movements across the sky, and many civilizations associated it with love and beauty. The planet was named after the Roman goddess Venus, and it seems fitting. From the outside, Venus appears elegant and serene. But beauty can be deceptive. As we approach Venus, the details of the cloud tops become clearer. The clouds exist in distinct layers between about 50 and 70 kilometers altitude, and they circle the planet at tremendous speed. While Venus itself rotates extremely slowly, One rotation takes 243 Earth days, longer than its 225-day orbital period. The upper atmosphere screams around the planet in just 4 Earth days. This phenomenon, called superrotation, creates winds of up to 360 kilometers per hour at the cloud tops. Why Venus's atmosphere rotates so much faster than the planet itself is another mystery. The clouds form intricate patterns. Even from orbit, Venus is clearly a world governed by atmospheric dynamics unlike anywhere else we know. Before we descend through those clouds to the hidden surface below, let's consider Venus's place in the solar system's story. Venus and Earth are often called sister planets because they're remarkably similar in size, mass, and composition. Venus's radius is about 95% of Earth's, and its mass is about 82% of Earth's. They likely formed from similar materials in the protoplanetary disk and should have had similar initial conditions. Yet somehow, these twin worlds evolved in completely opposite directions. Earth became a haven for life, with liquid water covering most of its surface and a thin, breathable atmosphere. Venus became a hellish greenhouse, with surface temperatures hot enough to melt lead and atmospheric pressure crushing enough to destroy submarines. What happened? Why did these sisters diverge so dramatically? The answer lies in a process that began billions of years ago and continues to this day: the runaway greenhouse effect. Young Venus may have actually been more Earth-like, with liquid water oceans and a much milder climate. Some scientists even speculate that Venus could have been habitable for the first 2 billion years of its existence. But Venus's proximity to the Sun, combined with the gradual brightening of the Sun over time, tipped the balance. As more water vapor entered the atmosphere, the greenhouse effect intensified. More heat was trapped, which led to more evaporation, which led to more greenhouse warming. It was a positive feedback loop with no natural break, and it transformed Venus from a potentially habitable world into the Inferno we see today. We're about to witness the end result of that transformation. Our spacecraft begins its final approach to Venus, preparing for entry into the atmosphere. Unlike Mercury, where we could simply land on the exposed surface, Venus demands that we descend through dozens of kilometers of increasingly dense atmosphere, each layer more hostile than the last. The clouds themselves are made of sulfuric acid droplets, corrosive enough to eat through metal and organic materials. Below the clouds, the atmosphere is almost entirely carbon dioxide, creating a pressure at the surface 92 times greater than Earth's atmospheric pressure. And the temperature? The temperature at the surface averages 465 degrees Celsius, hot enough to melt tin, lead, and zinc. Are you ready to descend into one of the most hostile environments in the solar system? Take a deep breath of your comfortable Earth-like air, and let's begin our descent into the veiled world. Our descent begins in the upper atmosphere, about 100 kilometers above Venus's surface. Here, temperatures are relatively mild, around minus 100 degrees Celsius, and the pressure is similar to Earth's at high altitude. The sky above us is black with stars still visible, but ahead and below, the clouds await like a wall of cream-colored fog. As we drop through 80 kilometers altitude, we enter the upper cloud deck. Sulfuric acid particles surround us, and the light begins to take on a strange, diffused quality. The sunlight filtering through the clouds scatters in all directions, creating an omnidirectional glow. Temperature and pressure are both rising noticeably now. We're descending into a realm that has destroyed every spacecraft that has attempted to operate here for more than a brief time. At 60 kilometers altitude, we're in the middle cloud deck, and conditions are surprisingly Earth-like in one respect. The temperature here is about 20 degrees Celsius, and the atmospheric pressure is about 1 atmosphere, the same as Earth's surface. This is actually the most temperate region in all of Venus's atmosphere. Some scientists have speculated that this zone could potentially harbor microbial life, floating in the clouds and feeding on chemical reactions driven by sunlight. The idea of life in Venus's clouds is controversial and unproven, but it's not impossible. The sulfuric acid is a problem, but some extremophile organisms on Earth can tolerate acidic conditions. If life exists on Venus, this is where we might find it. But we're not stopping here. We continue our descent into the depths. Passing through 50 kilometers, we exit the bottom of the main cloud deck and enter the lower haze. The clouds above us form a ceiling that blocks out all direct sunlight. From this point downward, no sunbeams will reach us. All light is scattered and diffused by the thick atmosphere above. The temperature has climbed to about 100 degrees Celsius, the boiling point of water at Earth's surface pressure, but the pressure here is already several times Earth's atmospheric pressure and rising fast. The lower atmosphere is surprisingly clear compared to the clouds above, but visibility is limited by the dense carbon dioxide and the heat haze. We can't see the surface yet, but we can sense it below us, radiating heat upward through the increasingly oppressive atmosphere. At 30 kilometers altitude, the conditions have become truly extreme. The temperature has soared to 200 degrees Celsius, and the atmospheric pressure is now 20 times Earth's surface pressure. Our descent vehicle's structure is beginning to creak and groan under the increasing load. The carbon dioxide around us is so dense that it's beginning to behave more like a fluid than a gas. Heat transfer from the scorching layers below creates convection currents that buffet our craft. Lightning flashes illuminate the murk around us. Each flash briefly reveals the thick, soup-like atmosphere that surrounds us, 15 kilometers above the surface, and the conditions are beyond anything experienced anywhere on Earth. The temperature has reached 350 degrees Celsius, hot enough to melt several types of metal. The pressure is now 60 atmospheres, equivalent to being 600 meters deep in Earth's oceans. The atmosphere is so dense that it provides significant buoyancy. Our spacecraft's descent has slowed dramatically, as if we're sinking through honey rather than falling through air. The visibility has actually improved somewhat because the dense atmosphere is clear of particles down here, though the intense heat makes everything shimmer and waver. We still can't see the surface clearly, but we know it's close now. Just a few more minutes of descent through this hellish environment. 5 kilometers from the surface, and the full horror of Venus's environment becomes apparent. The temperature is now 430 degrees Celsius, the pressure 85 atmospheres. Our spacecraft's cooling systems are working at maximum capacity just to keep the internal equipment from melting. Through the thick atmosphere, we finally catch our first glimpse of the surface below, a rocky, volcanic landscape glowing dull red from its own heat. The surface is illuminated by a dim, reddish-orange light filtered through all the atmosphere above, creating a perpetual twilight that scientists have compared to being under 900 meters of ocean water at dusk. This is as close to the classical conception of hell as anywhere in the solar system. And we're about to land on it. Our landing gear touches down on Venus's surface with a solid thud that you can feel through the craft's structure. We've made it. We're standing on the surface of the hottest planet in the solar system, in an environment more hostile than the interior of a pressure cooker combined with the inside of an oven. The surface temperature here is 465 degrees Celsius. Hot enough to bake a pizza in seconds, hot enough to make lead flow like water. The atmospheric pressure is 92 times Earth's at 92 bar, equivalent to the pressure experienced by submarines at a depth of 900 meters beneath Earth's oceans. Our spacecraft has perhaps an hour or two before the heat and pressure cause critical systems to fail. Let's make the most of this time and explore Venus's hidden world. Standing on Venus's surface is an experience beyond anything you could prepare for. The light is dim and reddish-orange, as if you're viewing the world through heavily tinted goggles. But unlike any twilight on Earth, this light is completely diffused. There are no shadows, no bright sources, just an omnidirectional glow from the atmosphere itself. The sky above you is a featureless orange-yellow, the clouds completely invisible from down here, too far above and obscured by the dense atmosphere. Visibility extends for perhaps a few kilometers before the thick air and heat shimmer make everything blend into a hazy orange blur. The landscape looks almost sepia-toned, drained of color by the filtered light and the uniform orange atmospheric glow. This is what sunset would look like if it lasted forever. The surface beneath your feet is solid rock, but rock unlike any you'd find on Earth's surface. It's basalt, volcanic in origin, similar to the rock that forms Earth's ocean floors and volcanic islands like Hawaii. But this basalt has been baked at high temperatures for billions of years, altering its properties. The heat is so intense that some minerals are near their melting points. Sulfur compounds give parts of the landscape a yellowish tint where they've concentrated. The ground is relatively flat here, but in the distance you can see rolling volcanic plains, and beyond them, mountains rising into the orange haze. Despite being the closest planet to Earth in size and composition, Venus's surface feels utterly alien, a place where no human will walk in the foreseeable future. Venus's surface is dominated by volcanic features. About 80% of the planet is covered by smooth volcanic plains formed by vast lava flows. These plains are relatively young geologically, perhaps only 300 to 600 million years old. At some point in Venus's history, massive volcanic activity resurfaced most of the planet, erasing older terrain and creating the landscape we see today. Unlike Earth, where plate tectonics continuously renews and recycles the crust, Venus appears to undergo episodic global resurfacing events. The entire planet's surface may be destroyed and reformed by volcanic activity every few 100 million years. You're standing on a world that was completely remade in relatively recent geological time, and it may happen again in the future. The volcanism may be dormant now, but Venus is far from dead. Rising above the plains are volcanic mountains, some reaching heights of over 8 kilometers. Maxwell Montes, Venus's highest mountain range, towers 11 kilometers above the average surface elevation. Taller than Mount Everest, rises above Earth's sea level. These mountains are thought to be volcanic in origin, built up by successive lava flows over millions of years. Scattered across the surface are hundreds of shield volcanoes, ranging from small domes to massive mountains. Some show signs of recent activity. The volcano? Idun Mons displays thermal anomalies, suggesting it may have erupted in the last few million years, perhaps even more recently. The thick clouds prevent us from directly observing volcanic eruptions, but Venus is almost certainly volcanically active today, adding to its already hellish atmosphere through volcanic outgassing. Among Venus's strangest features are structures called coronae. These are thought to form when hot plumes of magma rise from Venus's mantle, pushing the crust upward and creating these circular patterns before collapsing back down. There are also long, winding channels called canali that stretch for thousands of kilometers, possibly formed by flowing lava that was so hot and fluid it could travel vast distances before solidifying. And then there are the tesserae, highly deformed, fractured regions of crust that may be remnants of older terrain that survived the global resurfacing events. Each of these features tells us something about the geological forces at work deep within Venus's interior. Unlike Mercury's surface, which is completely dry and has been for billions of years, Venus's surface shows evidence of a lost ocean. Chemical analysis of the atmosphere reveals a ratio of deuterium to normal hydrogen that is about 100 times higher than Earth's. This enrichment in heavy hydrogen is a signature of water loss. Normal hydrogen escapes to space more easily than deuterium, so over billions of years, the deuterium became concentrated in what water vapor remained. This tells us that Venus once had significantly more water, perhaps enough to form oceans. But the runaway greenhouse effect boiled it away. The water vapor rose high into the atmosphere, where solar ultraviolet radiation split it into hydrogen and oxygen. The hydrogen escaped to space, while the oxygen combined with rocks on the surface. Venus's ocean evaporated into space, leaving this scorched desert. The ultimate cause of Venus's hellish conditions is the runaway greenhouse effect, and it serves as a stark warning about atmospheric composition and climate. Venus's atmosphere is 96.5% carbon dioxide compared to Earth's 0.4%. This CO2 acts like a blanket, trapping heat from the sun. Even though Venus's thick clouds reflect most sunlight back to space, the small amount that does penetrate is trapped by the carbon dioxide, unable to radiate back into space. The result is a surface temperature higher than Mercury's, even though Venus is almost twice as far from the sun. It's not proximity to the sun that makes Venus the hottest planet. It's the greenhouse effect. Understanding Venus's climate catastrophe helps us understand our own planet's delicate atmospheric balance and the importance of keeping our own greenhouse gas levels in check. Standing here on Venus's surface, surrounded by this hellscape, it's hard to imagine that this world might once have been habitable. But the evidence suggests it's possible. Recent computer models indicate that Venus could have maintained liquid water on its surface for up to 2 billion years after its formation. During that time, it may have had a temperate climate, shallow oceans, and conditions suitable for life. The sun was about 30% dimmer than it is today, which would have meant less intense heating. Venus might have rotated faster, creating day-night cycles that helped regulate temperature. Clouds would have reflected sunlight, keeping the surface cool enough for water to remain liquid. Young Venus might have looked remarkably like Earth. So what went wrong? The transition from habitable to hellish was gradual but inevitable. As the sun grew brighter over billions of years, as all main sequence stars do, Venus received more solar energy. The increased heating caused more water to evaporate from the oceans. Water vapor is itself a powerful greenhouse gas, so this created a positive feedback loop. More heat led to more evaporation, which led to more greenhouse warming, which led to more evaporation. Eventually, a critical threshold was crossed. The oceans began to evaporate faster than rain could return water to the surface. The water vapor content of the atmosphere increased dramatically, and the greenhouse effect intensified into a runaway process. Within perhaps a few 100 million years, Venus transformed from a water world to a steam bath to the dry inferno we see today. One key factor in Venus's fate may have been the lack of plate tectonics. On Earth, plate tectonics plays a crucial role in regulating climate through the carbon cycle. Carbon dioxide is removed from the atmosphere by weathering and chemical reactions with rocks, then subducted into the mantle at tectonic plate boundaries. Volcanoes return some CO2 to the atmosphere, but overall, plate tectonics acts as a thermostat, removing excess greenhouse gases over geological time. Venus, lacking plate tectonics, had no such mechanism. Once carbon dioxide entered the atmosphere through volcanic activity, it stayed there. Over hundreds of millions of years, volcanic outgassing added more and more CO2 to the atmosphere with no removal mechanism. The lack of plate tectonics sealed Venus's fate as a greenhouse world. Another contributing factor was Venus's slow rotation. Venus rotates once every 243 Earth days, and it rotates retrograde backward compared to most planets, meaning the sun rises in the west and sets in the east. This slow rotation is unusual and may be the result of tidal interactions with the sun or a massive impact early in Venus's history. The slow rotation means Venus doesn't generate a significant magnetic field like Earth does. Without a magnetic field to shield it, Venus's atmosphere is exposed directly to the solar wind, which strips away lighter atmospheric components over time. The slow rotation also means Venus lacks the day-night temperature variations that help drive atmospheric circulation on Earth. Everything about Venus conspired to create the extreme conditions we see today. Could Venus ever be habitable again? Some scientists have proposed terraforming Venus, deliberately modifying its environment to make it suitable for human habitation. Ideas include importing hydrogen from the outer solar system to combine with atmospheric CO2 to form water and graphite, or deploying massive sun shields to cool the planet. Some proposals suggest seeding the atmosphere with engineered microorganisms that could convert CO2 into other compounds. Perhaps the most audacious idea is floating cities in Venus's upper atmosphere where temperatures and pressures are Earth-like. These cities would float at about 50 kilometers altitude, suspended by breathable air, which is actually a lifting gas in Venus's dense CO2 atmosphere. It's science fiction for now, but Venus's clouds may be more hospitable than its surface. The story of Venus is ultimately a cautionary tale about planetary climate. Here was a world that may have been similar to Earth, that may have had oceans and possibly even life, but small differences in initial conditions and the inexorable brightening of the sun led to catastrophe. The runaway greenhouse effect is not just a theoretical concern, it actually happened on Venus, and the result is before us. While Earth is not in immediate danger of becoming Venus, studying Venus's climate history helps us understand the boundaries of habitability and the factors that keep a planet livable. Every measurement we make of Venus's atmosphere, every model we build of its climate, teaches us about our own planet's climate system and the importance of atmospheric composition in determining a world's fate. Several space missions have attempted to study Venus's surface, and all have been destroyed by the hostile conditions within hours at most. The Soviet Venera program succeeded in landing several probes that transmitted data and even images from the surface before succumbing to the heat and pressure. The Venera 13 lander survived for 127 minutes, a record that still stands. These brief windows of data gave us our only direct looks at Venus's surface. Future missions may use advanced materials and cooling systems to extend surface operations, but Venus will always be one of the most challenging environments to explore. As our lander systems begin to fail in the crushing heat, it's time to depart Venus and reflect on what these two scorched worlds have taught us. As we ascend from Venus's surface, fighting through the crushing atmosphere one last time, climbing through the sulfuric acid clouds, and finally emerging into the cold darkness of space, we can look back at both worlds we visited, Mercury and Venus. Mercury and Venus. Mercury. Airless and geologically dead, its huge iron core slowly cooling, its surface a cratered record of the solar system's violent youth. Venus, wrapped in a suffocating atmosphere, its surface hidden beneath clouds, geologically active and dynamic, its climate a runaway disaster. Two worlds, two very different paths, but both teaching us profound lessons about planetary formation, evolution, and the factors that determine whether a world becomes a haven or a hellscape. Consider their similarities first. Both are rocky worlds composed primarily of silicate rocks and metals. Both are terrestrial planets formed in the inner solar system from similar building blocks. Both orbit close enough to the Sun to receive intense solar radiation. Both have been shaped by volcanic activity at some point in their histories. And both are, by Earth standards, utterly inhospitable to life as we know it. Yet their differences are equally striking. Mercury is small and dense, with the largest iron core proportionally of any planet. Venus is almost Earth's twin in size, but has a vastly different atmospheric composition and climate. These differences arose from subtle variations in initial conditions and subsequent evolutionary pathways. Small differences early on led to radically different end states. Mercury's defining characteristic is its proximity to the Sun. orbiting at just 039 AU, it receives more than 6 times the solar radiation that Earth does and 14 times what Venus receives. This intense energy creates the extreme temperature variations between day and night that define Mercury's environment. The lack of atmosphere means there's no mechanism to distribute heat, so the day side bakes while the night side freezes. The proximity to the Sun also subjected Mercury to intense solar wind during its formation, possibly explaining its large core through the preferential removal of lighter elements. Everything about Mercury flows from its location. The first planet, the closest world to our star, forever locked in Sol's searing embrace. Venus's defining characteristic is its atmosphere. The thick blanket of carbon dioxide transforms a world that should be cooler than Mercury into the hottest planet in the solar system. The atmospheric pressure of 92 bar would crush a human instantly, and the temperature of 465 degrees Celsius would vaporize them shortly afterward. The sulfuric acid clouds add another layer of hostility. Yet this atmosphere also creates a strange stability. The thick atmosphere distributes heat so effectively that Venus's surface temperature is nearly the same everywhere, from equator to poles, from day side to night side. The temperature variations that dominate Mercury's environment are almost absent on Venus. The atmosphere is both Venus's most distinctive feature and the source of its extreme conditions. Everything about Venus flows from those thick clouds. Both worlds tell us about geological processes and planetary evolution. Mercury's lobate scarps reveal a planet that has shrunk as its core cooled, its crust cracking under the stress. Venus's volcanic plains and coronae reveal a geologically active world, possibly with ongoing volcanism. Mercury's surface is ancient, preserving a record billions of years old. Venus's surface is relatively young, having been completely resurfaced by volcanic activity. Mercury may be geologically dead now, all its internal heat lost to space, its core frozen or slowly freezing. Venus remains geologically alive, its interior hot enough to drive mantle convection and surface volcanism. Age and activity. Mercury represents the past, Venus represents ongoing processes. Together, they bracket the range of geological possibilities for terrestrial planets. Perhaps most significantly, these worlds teach us about habitability. Neither is remotely habitable now, but Venus may have been habitable in the past. This transformation from potentially life-bearing to definitively lifeless is one of the most important lessons of planetary science. It demonstrates that habitability is not permanent, that planetary environments can undergo dramatic changes over geological time. The factors that make a world habitable, the right distance from the Sun, the right atmospheric composition, the right geological processes to regulate climate, must persist for billions of years for life to emerge and thrive. Venus had some of these factors initially, but lost them. Earth has maintained them for 4 billion years. Understanding why makes us appreciate how fortunate we are and how fragile the conditions for life may be. Looking at Mercury and Venus together, we see two experiments in planetary evolution, two paths diverging from similar origins to completely different endpoints. We see the importance of initial conditions, of distance from the Sun, of atmospheric composition and retention, of geological activity and heat loss, of magnetic fields and solar wind interactions. These are the variables that determine a planet's fate, and we're only beginning to understand how they interact and what thresholds, once crossed, lead to irreversible changes. As we discover more exoplanets orbiting other stars, many of them likely similar to Mercury or Venus, The lessons we learn from our solar system's scorched worlds will help us understand those distant planets and assess whether any might harbor conditions suitable for life. The scorched worlds are our local laboratories for planetary science. As we journey back toward Earth, leaving the scorched worlds behind in the sun's glare, it's worth reflecting on what we've learned. We've walked on Mercury's cratered surface and felt the full force of solar radiation at its most intense. We've descended through Venus's toxic clouds to stand on a surface hot enough to melt lead, crushed by atmospheric pressure comparable to the deep ocean. We've witnessed two worlds that, despite being our closest planetary neighbors, are more alien than we might have imagined. These are places no human will visit in the foreseeable future, yet studying them from afar expands our understanding of what's possible in the universe and helps us appreciate our own planet's unique character. The scorched worlds are harsh teachers, but their lessons are invaluable. Mercury teaches us about extremes. It shows us how a world can experience the hottest and coldest temperatures in the solar system on the same planet. It demonstrates how the loss of an atmosphere, or perhaps never having a substantial one, leads to environments where temperature regulation is impossible. Mercury's huge iron core reminds us that planets can have compositions far outside the norm, that catastrophic collisions or unusual formation conditions can create worlds with unexpected internal structures. And Mercury's slow rotation coupled with its fast orbit creates day-night cycles unlike anything else we've encountered. Every strange characteristic challenges our assumptions about how planets should behave, forcing us to expand our models and theories to account for the full range of planetary possibilities. Venus teaches us about atmosphere and climate. It's a natural laboratory for studying greenhouse effects, showing us the ultimate consequence of runaway atmospheric heating. The fact that Venus is hotter than Mercury, despite being almost twice as far from the Sun, is a powerful demonstration that atmospheric composition matters more than solar distance in determining surface temperature. Venus shows us how positive feedback loops in climate systems can transform a world completely. It demonstrates how the loss of water and the accumulation of carbon dioxide can create conditions hostile to life, and the possibility that Venus was once habitable but lost. That habitability should serve as a warning. Planetary environments are not guaranteed to remain stable. Conditions favorable to life must be actively maintained through geological and atmospheric processes. Together, Mercury and Venus define the inner boundary of habitability in our solar system. They show us what happens when planets form too close to their star or when atmospheric composition goes catastrophically wrong. They bracket the range of conditions under which rocky planets can exist near a sun-like star. Between Mercury's airless, extreme temperature swings and Venus's thick, stable but hellishly hot atmosphere lies a range of possible planetary states. Earth exists in that range, having threaded the needle between too little atmosphere and too much, between too close to the sun and too far, between geologically dead and geologically stable. The scorched worlds help us understand Earth's place in this spectrum and what factors keep Earth habitable while its neighbors became wastelands. The exploration of Mercury and Venus has been achieved primarily through robotic spacecraft, and these missions represent some of humanity's greatest technological achievements. NASA's Mariner 10 made the first flybys of Mercury in the 1970s. The Messenger mission orbited Mercury from 2011 to 2015, mapping the entire planet and revolutionizing our understanding. The European-Japanese Bepi-Colombo mission, launched in 2018, is currently en route to Mercury with even more sophisticated instruments. For Venus, the Soviet Venera program achieved the remarkable feat of landing multiple probes on the surface, returning images and data despite the crushing conditions. NASA's Magellan mission mapped Venus's surface with radar in the early 1990s. Future missions are planned for both worlds, driven by our desire to understand these extreme environments and what they tell us about planetary evolution. Why do we study these inhospitable worlds? The answer goes beyond simple curiosity. Understanding Mercury helps us understand planetary formation, the role of impacts in shaping worlds, and how planets lose heat over billions of years. Understanding Venus helps us understand atmospheric physics, climate science, and the boundaries of habitability. Both planets serve as test cases for our theories of planetary evolution. They also have practical applications. The money and effort spent studying these worlds yields insights that help us understand and protect our own planet. The scorched worlds, though distant and hostile, are directly relevant to humanity's future. As we approach Earth, our blue marble growing larger in the view screen, the contrast with the worlds we've just visited becomes overwhelming. Earth has liquid water covering most of its surface, something neither Mercury nor Venus possesses. Earth has a breathable atmosphere with just enough greenhouse effect to keep temperatures moderate, unlike Mercury's vacuum or Venus's crushing blanket of CO2. Earth has active plate tectonics that regulate climate over geological timescales, a process absent on both scorched worlds. Earth has a strong magnetic field protecting it from solar wind, unlike Mercury's weak field or Venus's complete lack of one. Every factor that makes Earth habitable stands in stark relief when compared to our neighbors. We are indeed fortunate beyond measure to call this world home. Our spacecraft glides into Earth orbit, and the sight is breathtaking. After the grey, cratered desolation of Mercury and the cloud-shrouded Inferno of Venus, Earth appears almost impossibly beautiful. The deep blue of the oceans, liquid water, something we saw nowhere else on our journey. The white swirls of water vapor clouds, benign weather systems, not sulfuric acid, death shrouds. The green and brown of continents, land masses shaped by erosion, tectonics, and life itself. This is what a habitable planet looks like. This is what 4 billion years of stable climate, active geology, and protective magnetic fields create. Earth is not just our home. It's a rare jewel in a solar system of extremes, a sanctuary of moderate conditions in a cosmos that tends toward hostile environments. Look at Earth's atmosphere, just thick enough to protect us from radiation and meteorites, to distribute heat and create weather, to provide pressure for liquid water to exist on the surface. Not too thin like Mercury's exosphere, not too thick like Venus's crushing blanket. The composition is perfect. 78% nitrogen, 21% oxygen, with just traces of greenhouse gases to keep temperatures moderate. This atmosphere is largely the product of life itself. Billions of years ago, photosynthetic organisms began producing oxygen, gradually transforming the atmosphere from one that would suffocate us to one we can breathe. Earth's atmosphere and Earth's biosphere co-evolved, each shaping the other. It's a system of staggering complexity and balance, maintained by countless feedback mechanisms. The scorched worlds have no such systems. Earth's magnetic field, generated by our planet's liquid iron outer core, creates the magnetosphere that shields us from the solar wind. This invisible protective bubble extends tens of thousands of kilometers into space, deflecting charged particles that would otherwise strip away our atmosphere and bombard the surface with harmful radiation. Mercury has a weak magnetic field that provides minimal protection. Venus has none. Earth's magnetosphere is one of the key factors that has allowed complex life to evolve here. Without it, our atmosphere would gradually be eroded by the solar wind, and the surface would be bathed in dangerous radiation. We live our entire lives under the protection of this magnetic shield, never seeing it, rarely thinking about it, yet utterly dependent on it for our survival. Earth's water cycle is another marvel absent from the scorched worlds. Water evaporates from the oceans, forms clouds, falls as rain over land, flows through rivers back to the sea, and the cycle continues endlessly. This cycle moderates temperatures, distributes heat from the equator to the poles, weathers rocks and contributes to the carbon cycle, and provides the medium in which life exists. Mercury has only isolated pockets of ice in permanently shadowed craters. Venus lost all its water billions of years ago to space. Earth has maintained its water for over 4 billion years, and that water, the same water that filled primordial oceans, flows through your body right now. Every drop of water you've ever drunk has cycled through this system countless times. We are water beings living on a water world. Earth's plate tectonics, the slow motion of continental and oceanic plates, is unique among the rocky planets we've visited. This geological activity creates mountains, causes earthquakes and volcanic eruptions, and most importantly, regulates Earth's climate over millions of years through the carbon cycle. Plate tectonics is likely one reason Earth has remained habitable for billions of years while Venus did not. The system works like a planetary thermostat, removing excess CO2 when the planet is too warm and releasing it when the planet is too cold. It's a slow process taking hundreds of thousands of years, but it's kept Earth's climate within a range conducive to life through ice ages and warm periods alike. The ground beneath our feet is in constant slow motion, and that motion helps keep us alive. Perhaps the most remarkable difference between Earth and the scorched worlds is life itself. From bacteria in hydrothermal vents at the ocean floor to birds soaring in the upper atmosphere, from microscopic plankton to massive whales, from desert extremophiles to rainforest ecosystems bursting with diversity. Earth teems with life in every niche, every environment, every available space. Life has transformed this planet, creating the oxygen atmosphere, altering the chemistry of oceans and land, even affecting the albedo and climate. Life and Earth have co-evolved for nearly 4 billion years, each shaping the other in an intricate dance of adaptation and modification. As far as we know, Earth is the only planet in the universe where this has occurred. We found no evidence of life on Mercury, Venus, Mars, or anywhere else. We may be alone, or life may be rare. Either way, Earth's biosphere is precious beyond measure. Journey to the scorched worlds has given us perspective. We've seen what happens when a planet is too close to its star, when an atmosphere is lost or becomes too thick, when geological processes cease or fail to regulate climate, when water is absent or evaporates away. We've witnessed the cosmic experiments that created Mercury's iron heart and Venus's greenhouse hell. And through it all, we've gained a deeper appreciation for Earth, for the delicate balance of factors that make this world habitable, for the complex systems that maintain that habitability, for the life that flourishes here. We are extraordinarily fortunate to exist on this pale blue dot, suspended in a sunbeam, the only home we've ever known. The scorched worlds remind us that Earth's habitability is not inevitable, not permanent, and not to be taken for granted. Our planet is a miracle, and it deserves our protection and care. Our voyage to Mercury and Venus has come to an end, but the lessons of the scorched worlds will stay with us. We've walked on surfaces where lead melts and stood beneath skies of sulfuric acid. We've seen the iron heart of the messenger and witnessed the greenhouse inferno of the veiled world. We've learned that planetary environments can be hostile beyond imagination, and that Earth's habitability is a rare and precious gift. As you close your eyes and drift towards sleep, remember that you live on a world of unimaginable beauty and perfect balance, a sanctuary in a cosmos of extremes. What does it mean to you, knowing that our planet is so rare, so fragile, and so extraordinary? Sleep well, cosmic traveler, under Earth's protective atmosphere and magnetic shield, cradled by the only world we know that welcomes life. Until our next journey among the stars, may you find peace in knowing your place in this grand cosmic story. Good night.